thanks to David Silver, I can skip my first 10 slides, which tries to convince you that StarCraft is a good idea. Yeah, so when I made this slide, like 10 years ago for the 2011 AIIDE conference, there were less check marks here. So, like, Go had not beaten the world champion yet. But then AlphaGo came around, and now computers are better than the world champion at Go. And there's sort of this question mark here next to the StarCraft image with DeepMind's AlphaStar program. They've gotten pretty close to beating professionals, but still not yet the world's best professional. We have lots of time, so I'll just give people a chance to sit down. All right. So we have StarCraft, which is this huge, huge game. If you saw, did anyone not see David Silver's talk yesterday? Okay, Santi, you know what StarCraft is. So StarCraft is this huge, huge game. It has exponential action space, more states than the number of atoms in the universe to the power of 100. It's just crazy, crazy big. So what we've done traditionally is take StarCraft and decompose it into a bunch of sub-problems. And the way we've done this is mimicking sort of how humans have played and practiced the game over the years. So for example, there's like knowledge and learning, opponent modeling, strategic stances, army compositions, combat, unit placement, multi-agent pathfinding, all the typical things that you would find papers written about StarCraft on. This paper is going to focus on the build order planning side of things, and I'll get into what a build order is and what planning means in that respect. But of course, thanks to DeepMind, here's the question, what about AlphaStar? AlphaStar doesn't decompose things into sub-problems anymore, like just be AlphaStar, right? So of course, AlphaStar uses these giant neural networks to play the full game. It uses some domain knowledge, but basically, giant neural network that plays the whole game of StarCraft, and admittedly is by far the best StarCraft playing system that we know. If you took the best bots from the Brood War competitions and somehow translated them into StarCraft 2, I am confident that AlphaStar would win 100% of the games. It's really, really good. But with the question, why not use what AlphaStar is doing, just consider this. So I work at Memorial University. Our operating budget last year was $369 million Canadian. No offense to DeepMind, but they lost more than double my university's operating budget last year. So I cannot catch up to them at scale. It's impossible. Even if I had $700 million, my grad students wouldn't know what to do with it. I still need the David Silvers, right, and all these people. So it's impossible for anyone in this room to catch up to what DeepMind has done by trying to build a larger neural net or by trying to replicate their results. Not only that, but something I care about, for example, this article that was published back in June, is that with a lot of electricity comes a lot of environmental impact, right? So this is my excuse kind of not to use gigantic neural nets. Like, I couldn't do it if I tried, but there's an environmental impact, and it takes up to millions of dollars to train these neural nets in the cloud, right? So infrastructure, electricity, money, these are all important things that academics don't really have as much access to. And so my idea with my research recently is let's go smaller. Let's see what we can do with the simplest ideas. And on all three reviews, the negative thing about this paper was the idea is too simple. Well, I'm sorry, I'll make it more complex next time. So, build order planning. In order to explain what we did for this paper, I have to kind of explain what I did in 2011. So what is a build order and how do we plan it? So a build order is essentially a sequence of economic actions that you take in StarCraft. It's a list of buildings or units that we want to build in order to get some army composition. And what players do is they memorize these kind of opening books like build 4 probes and a pylon and then a gateway, et cetera, et cetera. So in the previous work, what we did was we used heuristic search, and we fed into this search a goal was a vector of unit type counts. So here's the army I want to have. here's what I currently have. Give me the build order that most quickly gives me that army, right? And so we get some build order sequence out. The problem with this was that we had to have another system which figured out what that army composition should be, right? So I had a bunch of hard-coded rules that said, if it's this far into the game and they have these units, then I want these units, etc. So just deciding what I want to build is a hard problem, let alone how to build those things. Of course, in order to do heuristic search, one of the downsides of search is that you need a model, and we don't have access to the StarCraft source code. The libraries out there can't save or load states very well, and so we had to write our own build order simulator. This is out there, it's free to use, it's called BOSS, it's the build order search system. And it's essentially just like a subset of the StarCraft engine that just does build order stuff. Okay? So if you want to do build order stuff in StarCraft, you can use our system for that. It has some nice properties. It's written from scratch in C++. You can modify it. It loads all the unit data from an external file, and it can simulate both Brood War and StarCraft 2. So if you want to do build order stuff in either, we have a library for that. It doesn't rely on any of the APIs, so it's just like the standard library for C++. And it can be used instantaneously in any competition bot, and it's been used by dozens of bots over the years. The algorithm that we used it's a depth-first branch and bound algorithm. So just picture standard recursive depth-first search, very, very simple algorithm, except we bound it on some bound, which I'll talk about, and we can prune it based on some heuristics. The really good things about this type of search is extremely low memory usage. It's linear with respect to the depth of the search. It's an anytime algorithm, which I'll explain in a second. We can save and load the search at any time, and we can use upper and lower bound heuristics to prune the search if we have them. So this is just an example search tree. You don't need to read. These are just unit types. This is the build order search tree. Okay? And what I meant by any time is that we start the search, and at some point we produce some solution. Okay? So we get our first solution. Gradually over time, we keep producing better and better solutions until we get to the optimal solution. But the good thing about this algorithm is that you don't have to wait until the best possible solution has been found. If we have some time limit, we can just stop the search at any point, and we can use the best solution up to that time limit. So unlike A star, for example, we don't have to wait for the only solution to be found. We can stop at any time and use one of the gradually increasingly good solutions. So the title starts with the word robust. What do we mean by robust? Well, this was the previous system. And like I said, the important thing here is we had to give it a very specific goal. Like, I want 3 Marines, 2 tanks, and 1 battlecruiser. But how do we get that? That's a very hard problem. Maybe you use machine learning, maybe you use something crazy. We use rules. Those rules took me dozens of hours of guess and check, and I'm not the best StarCraft player. But it's a problem to try and come up with that. So what we did in this paper is just say, let's take these very explicit rules and replace it by some abstract concept. For example, let's get the most firepower. That seems like it's a good thing. Really, really simple idea. So how do we maximize firepower? What exact formula are we using for evaluation here? There's a bunch of ways to do this. We could use, let's say, the damage of a unit. We could use the damage per second of a unit. Maybe we just take the number of units in our army, etc. What we chose to use, and this is just a first step. You can go as deep as you want with this, but what we chose was the resources that we have spent on army units. Okay? So I give an example here. Does this have this? Yay. Okay, I told you to look at this, but I'm pointing over here. So for example, Zealots are a Protoss unit. They cost 100 minerals each. And so if we have 3 Zealots, then our army value, that's the term we're using, is 300, because we have 3 things that cost 100 minerals. And what we're hoping here is that the prices of the units in the game have been balanced by the game designer such that this army value is sort of balanced, right? But of course, it doesn't take anything else into account. This is just the first step. So for example, it doesn't say, whether these are ground units or air units or invisible units. So there's a bunch of things that this is missing. But it turns out it still works pretty well. Yeah?
When it comes to the cost of the army or the value of the army, are you aiming for an army large enough with a high price, or just...
I'm looking to maximize this number.
So the army should cost, have a high cost?
I'll tell you the exact thing in another slide. I don't have a ton of time. I'll be happy to talk to you about it after. All right, so here's the exact problem statement. Choose some time t in the future. Produce the build order which maximizes the total army value at time t. That's my statement. That's what I'm trying to do. And so the idea is that if StarCraft has been kind of balanced well, that an army with a bigger value in terms of what we've defined is better than another army that has a lesser value. Of course, we all know that that's not true, but let's see how it works. Spoiler alert, this might be bad. Why is it bad? Okay, so let's take time t to be 4,500 in-game StarCraft frames, which is approximately 3 minutes. So we'll say, hey, build order search. Go 3 minutes into the future and produce the build order which maximizes the army value at 3 minutes into the future. What you'll see if you do this is you build absolutely nothing but economic units, and then you build up an economy, and then you start to build army units, right? That can be really bad. If you build absolutely no army units for the first little bit of the game, and then build them all at the end, well, what can happen? So, let's pretend that we found the maximum possible obtainable army value at any time during the game. And that's what this red line is. So if you have the absolute best build order at every time during the game, this is the maximal obtainable army value at any point, up until 3 minutes into the future. So, what the problem is this. Someone could have chosen this build order against our build order and had a 3 times bigger army at that given time. So we can use these build orders to visually inspect some sort of notion of exploitability, right? Even though we're maximizing the army value up until some certain time, another build order at a different time could have gotten something better and just wiped us out. So, what can we do to try and alleviate this problem? Well, the whole idea of this paper, summed up in one sentence, is let's instead maximize the area under this curve up until a given time. And intuitively, that should fill out those missing gaps, right? And we see here, this blue line represents the army value over time of the build order which maximizes the area under the curve rather than just the obtained value. So what we see here is, of course, we don't get quite as high at 3 minutes as the army value produced by the build order which only wants to maximize for that specific time. But the area between the blue curve, which is our build order, and the red curve is much, much, much less. So we're far less exploitable over time with this build order than other build orders. Oh my God, I've taken so long. All right. All right, so I have two things that I'm going to test. Boss IM, that's this integral maximization, area under the curve, and boss UG. UG just means the unit goal search. So UG is the old thing, IM is the new thing. My experiments. So, in order to test this out, I took UAlbertabot, which is our really nice modular bot. I replaced the build order system. All I did was take out boss UG, which is what we used before, and replace it with this new system. So take out the unit goal search, put in the integral maximization search. We used the random race, so we tested all races with this. The bot attacks as soon as possible, and then uses combat simulation to retreat if it thinks it's going to lose. So there's no attack timings, it's completely generalized. And essentially, we just do a new build order when the current build order is empty. All right. So, a lot of text on this slide, but essentially, UAlbertabot, UG, is the old UAlbertabot, and UAlbertabot IM is the new version with this new integral maximization. The old version had like dozens of hours of me hand-coding rules, which I completely took out just to replace with this integral maximization search. And we're looking 3 minutes ahead into the future at any given point. The first experiment that I did we used the 10 maps from the IEEE competition. I played 50 games versus the retail AI against each of the 3 races of the retail AI on each of the 10 maps, so we played 1,500 games. This is a standard benchmark. If you can't beat the retail AI, your bot sucks, right? So I just wanted to make sure that it worked before I played it against real bots. The old system won 1,494 games out of 1,500. The new system won 1,488. And those 6 extra losses were to the Dark Templar rush of the in-game AI that it sometimes randomly uses, and it's because we're not specifically doing anything against invisible units. Remember I said that that's a problem? Well, you can improve that if you want, but it used a strategy that this is particularly weak against, but still have like 99% win rate. All right, this is the real experiment. We reran the complete 2017 AI IDE StarCraft competition. 2017 because at the time of doing the paper, that was the most recent one. The exact settings and hardware were used as the actual competition, and I know because I ran the actual competition and we used the same hardware. We ran UAB, UG, and then IM. And what we did was, because running the entire competition takes 24/7, 3 weeks, what we did was just run the top 10 bots from that competition against our bot, just to see how it would do. And a lot of the bots, like the bottom half of the competition, they were trash, so we didn't want to test against them anyway. All right. So what happened? The dotted line is the old UAlberta bot, and the solid line is the new one. And we improved our overall win rate by almost 10%. And just to give you an idea of how much that matters, in that competition, 4th place and 10th place were separated by 7%. And so 10% win rate improvement is gigantic. Now, it still wouldn't have won the competition. I haven't actually updated that bot in like 5 years, but it did much better than the previous system, which had a bunch of hard-coded rules in it. Not only that, but you can see the old system, the win rate went down over time. And that's because bots are able to actually learn in this competition, and so they can memorize the build order that you did and then completely counter it the next time. And so you'll find that the learning bots exploit the weaker bots over time. And it turns out that our win rate here kind of stayed more stable, and so I think it's probably less exploitable because it's trying to maximize this army value rather than a very specific hard-coded set of units, which is easy to exploit. And if we look at, so these are the 10 bots that we tested against. If we look at only the results against the top 5 bots, our win rate basically doubled or more against the top 5 bots. And so I don't know if this is a general statement, but from our experiment, it seems that there was more improvement versus the stronger bots than against the weaker bots. So it seemed to work. So conclusions. The new system outperformed the old system in this test. It doesn't rely on any hand-coded goals other than the fact that we're trying to maximize this formula that we hand-coded, which is army value. It runs in real time in a competition setting with 0 offline training time. Okay? And if we reran the competition and we completely randomized all the properties of all the units, this would still work. Right? Do that, AlphaStar. Right? So that's one benefit of search, is that in real time it finds the best-ish thing. So, some future work. We could definitely use a better army value function. Perhaps we could use our combat simulator to run a simulation instead of just wanting this one number. We should factor in special unit properties at some level in order to make the best system possible. We could put some heuristics in. I did not have any pruning heuristics in this search. They could only make things faster and better. And the reviewers said, it's too simple, so we'll be sure to make things more complicated for the follow-up paper. Thank you.
Probably we have time for only one question. Any question to...
Sure.
So in your system, you define basically this level of abstraction of build orders, right? So your bot sees the game at different levels of abstraction, like controlling the individual units and also having these high-level like macro actions of the build order, versus Alpha Star that is very raw, right? It learns all the actions, it learns how to play the games from the individual low-level actions. So do you see any way to combine both approaches in a way that you can incorporate this build order search into this reinforcement learning?
Well, the good thing about AlphaStar is that you don't need the game engine, right? If you do any sort of search like this, you need some way to save and load states and do backtracking and all that sort of thing. So perhaps if they devoted some resources into learning a model of the game, then we could use that for the search. But I can't see myself just plugging this into AlphaStar and making it better. Yeah. Thanks.
The authors of the paper titled A Self-Play Policy Optimization Approach. Here. Okay, so we have all the presenters. So for regular papers, try to finish your talk in 15 minutes so that we have...
Okay, I'll try.
Okay, here is our second presentation today. Beating uncertainty in racing bot evolution to enhance exploration and pole position selection by
Antonio.
Antonio.
I'm the second one.
Okay.
Okay, good morning. Thank you everybody for being here. My name is Antonio. I'm from Spain, from the University of Granada. And I'm presenting this amazing work. I have to say this, but it's beating uncertainty in a racing game, in racing bot evolution, through enhanced exploration and pole position selection. Sorry, because I haven't found the time to include this sound on the presentation. Let's start. I'm going to follow the title because it's very representative of what we have done. So let's start talking about our racing bot. It's enclosed in an open source racing car simulator. I guess most of you know it. It's called Torx. It was used in several competitions for artificial intelligence as a test bed. But unfortunately, these competitions ran out I think in 2015, but we like the scope, the framework, and we like to solve this problem even now, because we think that if we found a very good solution, it could be possibly used in a real autonomous car, of course with several transformations, but could it be used? So in this environment, we have as input a set of sensors surrounding the car, saying the distance to different obstacles in the near distance, and the actuators are steer, brake, accelerator, and gear of the car. This is how Torx looks like. It's not very attractive graphically, but it's very powerful. It has realistic physics, for instance, very realistic, I have to say. So it's a very nice environment to work. Our controller is based on the standard controller architecture, but we have worked on two different subcontrollers. One devoted to set the target speed of the car, and the other one controlling the steering of the car. Okay, so the steering angle that we can use in our car. We used for each subcontroller a Mandani fuzzy system with 3 trapezoidal membership functions, one for the low values, medium values, and high values. And here you can see the sensors we are using in our car. There are a whole set of sensors surrounding the car that we just use three sensors. The front M5, which is minus 5 degree and 5 degree angles, and MT, which are minus 10 degrees and 10 degrees angle. The target speed fuzzy subcontroller uses a set of fuzzy rules to set the target speed depending on the inputs received in every sensor. And the steering control is also similar, but the rules just decide about the angle between 0, which is straight, and 1, which is 90 degrees. Evolution is because we are applying a genetic algorithm to improve this system, to improve these fuzzy rules. And we work on the definition of the membership functions, which are defined, using some parameters, as you can see here in this image, x1, x2, 3, and 4. So we work on these parameters to define the trapezoidal function, membership function. So I guess all of you, or most of you, know what a genetic algorithm is. It is an optimization algorithm, biosphere algorithm, inspired in the evolution of species, and which works with a population of possible solutions, which are evaluated somehow. You set a fitness value for every single solution to say how good it is. Then, according to this fitness value, you select the best individuals to be parents of the following population. Then you combine them in operators application. You combine these individuals to generate an offspring, to generate a set of descendants that normally are better than the parents. Okay? Then you replace bad individuals for good individuals normally, and you repeat this process until you reach a stop criteria. So what we have worked here in this work is in the evaluation part and also on the selection step. The population we are working with, the individuals, is a set of variables, of floating point variables, defining the different membership functions for each one of the inputs. For front sensor, max 5 and max 10. The evaluation of every single controller, every candidate, is just put our car with this configuration on the game and compete against other cars, or just make a solo race. We get then, in this image, we get then some outputs from torques, and we use these values to compute the fitness value of the individual. How we compute this fitness value? We use this formula. We try to maximize average speed on the track, on the race, okay, which is a compromise between the speed in the difficult parts, which is the low speed, and the speed in the easy parts of the track, which are the straight parts, which are maximum speed parts. So we combine them, we compute the average speed, which combines both of them, and we divide this value by the obtained damage by the car, because if the car gets too much damage, it is eliminated. It cannot finish the race. So it's a very important term to consider in an evaluation. Uncertainty. I guess all of you know what uncertainty in this scope of video games is. In this case, we are talking about uncertainty in several different ways, but we refer to the possibility that a very good driver, a very good controller, could be evaluated as a bad one due to external factors, such as the weather conditions in the track or an unexpected behavior by one of the rivals, for instance. So a very good controller is evaluated as bad one, and the other way around. A very bad controller could be evaluated as a good one because maybe two rivals are very good, they crash, and your controller, which is not so good, finishes the first one. Okay? So this is uncertainty, and also it is quite difficult in this kind of algorithm to determine that the fitness function, the fitness value, really represents a very good individual, a very good controller. So we have to take this into account also. To deal with this, we consider just in the fitness, as I have said, the main factors, just speed and damage, the main factors of the different outputs we can take from torques. We repeat the evaluation in several races, so unexpected behaviors are likely not to happen every time in different races, and several laps for the same reasons. And we also train our controllers without any rival, because we want that the controller learns to play by itself, not with external noise or uncertainty sources. And we also have selected a track combining different kinds of parts, difficult and easy parts. How we have enhanced exploration? We have used the so-called blend crossover operator, BLX alpha, which is a crossover which is allows us to control the balance between exploration and exploitation in the search. So at the very beginning, in a genetic algorithm, it is important, it is recommended that the algorithm explores the whole space of solutions. So we use a high value for alpha to potentiate the exploration. And at the end, in the last generations of this process, we reduce the value of alpha to go to a higher exploitation. We have implemented two different approaches. One, doing this, where alpha is variable, is high value at the beginning and low value at the end of the evolution, and another approach with alpha constant at a 0.5 value. So there is a balance between exploration and exploitation. What's pole position selection? Well, it's about this is about trying to evaluate individuals, to select the best individuals, not only based on the fitness, because the fitness is risky, as I have said. It's an uncertainty source. So what we do is to group the individuals in 10 individuals compete in several races, in several laps also, and using an F1 inspired score system, we assign a score to every car, every individual in every race, and we compute a number. So the best 5 at the end of this process are selected as parents for the following generation. The advantages of this approach is it is less sensitive to uncertainty because it's a fitness-less selection. It doesn't depend on the fitness. So after repeating this process on the generations, we can assure more or less that the best individual will survive. And how can we demonstrate that we are beating this problem? Well, the experimental setup is as this. These are the genetic algorithm parameters. The operators of the genetic algorithm, random initialization. We use a race-based selection, but unfortunately, because of due to time restrictions, we just apply it every 5 generations instead of every generation. That could be, more recommended, but it takes a lot of time to evaluate or to perform this race-based selection, pole position selection. The rest of the generations, we apply tournament selection, non-uniform mutation, and the 2 approaches of BLX alpha crossover. In the race-based selection, we consider 10 controllers, Alpine track 2, and 5 races, 20 laps each. And the starting grid in every race is random. So, how we select the best at the end of every run? We consider the 10 best individuals according to their fitness in the last generation. We run 5 races with 5 laps, and we select the best of these individuals in this last evaluation or race. And at the end of 10 runs, because we repeat this 10 times for each configuration, we select the best of all, again doing the same. We take the 10 best controllers and we repeat this evaluation, this race-based evaluation. The results. GFC is our previous controller, and GFCRS is our previous controller with race-based selection, and the FA and VA are the approaches applying BLX alpha constant and variable approaches. So, as we can see in the table, maybe in the table is not so clear, but I put an image right now in the image. As we can see, GFC FBA, which is the variable approach of BLX alpha, outperforms the rest. Get a very high score, clearly beating our previous approach, which is this one, and clearly beating the standard bots in torques, which are Taita, Inferno, and Bernit, for instance. We get a very good performance, even in an unknown track, which is E-Track 5, the orange results. So we get a very good score, even in a track that the car haven't been trained before. I have to say sorry to Diego, but I think he's not here. And I have to improve my Photoshop skills, as you can see. Well, we have considered a new challenger in this approach. We have baptized as PSRA for the first letter of the surnames of the creators. And it was created by Perez, Libana, Recio, Saef, and Isasi for 2009 competition. I know it's old, but believe me, I have sent hundreds of emails to several people asking for a controller, and just they send me their controller. So it's the one we have considered. They use a finite state machine using fuzzy rules. It is optimized by means of NSGA2, and they use also a classifier for predictions of parts of the track. So the results against this controller are very good also for our approach. So if you see the average speed is 20 kilometers better, 23. The maximum speed is around 15 kilometers more per hour. Damage, it's much better in our approach, and in both tracks. In Alpine 2, which is the track where we train the bot, and eTrack 5 also. So our bot with the variable approach is the very best and beats PSRI in 3 out of 5 races and in 4 out of 5 races. So, as a conclusion, we have beaten uncertainty in racing bot evolution through exploration and pole position selection, as we said in the title. And the future work is to implement this race-based selection in all the generations, and optimize, maybe apply optimization in the output of the rules, which is right now is hard-coded. I mean, the target speed is hard-coded, for instance, and the steering angle, and also optimize the set of passive rules, maybe generating them using genetic programming. So that's all. Thank you very much.
One or two questions.
Everything is clear.
So at one point, when you talk about pole position selection, you say that that's a fitness-less score. However, you do use the final position as so on this Formula One inspired scoring. So wouldn't that be considered some sort of fitness function?
Could it be? But it doesn't depend on. Well, it doesn't depend on a computation of different values obtained of the simulator. Let's say.
Okay.
The thing is, because we repeat the race several times, we decided to use this score function. But we could use just one race and select the winner, for instance. So it's a completely fitnessless. Doesn't depend on any number, just the position. But we repeat it several times, so we compute a sum of the results.
Okay,
Okay.
thank you.
Maybe let's discuss with him after this.
Yeah, thank you.
Is this yours?
So then the third presentation today, policy-based inference in trick taking card games. Yes. By Douglas.
Okay, for sure. Awesome, thank you.
Okay. So hello everyone, my name is Douglas Rebstock. I'm from the University of Alberta in Canada, and I'm going to be showing off my work in policy-based inference and trick-taking card games. And I did this work with Christopher Solinas, Michael Buro, and Nathan Sturtevant. So the goal today is just to show off this policy-based inference algorithm demonstrated in a trick-taking card game called Scott. So I'll go over some background, introduce the policy, inference algorithm, show its effectiveness directly in inference, show some experimental results in some gameplay of this game, and go on to the conclusion future work. So as most of you would already know, imperfect information games, in them there's some of the information is private, so this makes decision making quite difficult. So here's an example of checkers. It's an example of a perfect information game. So in these kinds of games, all the information that you need is presented to you at all times. So you can make your decisions from that. So in checkers, you have the board in front of you. Turns are taken sequentially. So you can do some kind of a search-based method that there's a lot of well-known algorithms for that. Whereas a game like Uno, you have your cards, the opponents have their cards, and you have to reason what cards they have to make decisions. So the private information is, would be in the hands, and this creates an information set. So for the private information that you have, there are a lot of different possible states that the other cards could be in. So you have to reason upon these states in this information set, and this is what I'll be loosely referring to as inference in this talk.
So trick-taking card games are they're a type of card game with a few general principles. Players will alternate playing cards to win tricks, and they have a goal of winning these tricks to win the game. So in these games, there's usually they're very large, and there's lots of hidden information, and this hidden information is slowly revealed through the process of this game. And this last property makes certain types of search-based algorithms quite effective and inference quite effective. I won't go into those properties in depth just to do the time limitations. And some examples of these games, Scott, Contact Bridge, Heart, Spades. And the domain that I'll be looking at today in this talk will be specifically Scott. So Scott is a popular German 3-player trick-taking card game, and there's 2 main parts, bidding and declaration followed by card play. And the winner of the bidding plays against the 2 other players, so it's 1 player against 2. And there's 3 main game types, suit, grand, and null. I won't go into the details of these, but just there's a lot of different rules in this game. And then the tournament points, which will come up in the experimental section. Basically, if you win the game, you get the value of the game plus 50 points, and if you lose the game, you lose the value of the game times 2 and minus 50 points. So it's quite expensive to lose a game of Scott. And here's just a quick example of the game. You don't need to follow along the rules perfectly. This is just to display the mechanics. So each player gets 10 cards each with 2 cards in the Scott. And then a bidding process happens. So player 2 and player 1 bid against each other until player 2 wins that bidding. And then player 2 bids against player 3. And this continues until player 3 passes. So player 2 is now the soloist against the 2 other players. And then the player 2 picks up the cards, decides on the game type, and the game would start. And then cards are just played sequentially for a trick. The winner of the trick starts the next trick. And this process will continue until the game is over. So here are the 10 tricks in the game. And yes, that would be a full hand of this game. So then in the scoring phase, just to see the value of the tricks, and if you've surpassed a certain value, in this case, getting 64 points. So there's different values associated with different cards. You would win the game. Or if you got below 60 points in this example, lose the game. So trick-taking card game, there's bidding and declaration, and then there's card play. So the work that I'm going to be comparing this against is work done by Buro et al. Originally in 2009, with more updated work by Solinas et al. In 2019. And it's the card player is called Kermit. So this plays Scott, and it's the current state of the art, and it plays a human expert level. And I'm going to be specifically looking at the card play. So in the card play for this player, it uses perfect information Monte Carlo search. So in perfect information Monte Carlo search, so there's lots of different states in the information set. It will randomly be selecting different states and evaluating the different actions for each state for that sampled state, and then it does this repeatedly. So here's just a quick example to motivate it a bit better. So the unknown cards, these are the opponent's cards. These are the possible ones. So we sample one, and then we just get the evaluations for the different possible moves for us, and then we repeat this process. And this process you can iterate as many times as you want, but at the end you just pick the action with the highest value. So in this case, 2 iterations, the king. So the key bit here that relates to the work is that this sampling of the different states, you can bias this using inference, and if you do this, if you bias this towards more the proper real distribution that the cards would be in, you'll get better results. So this brings us to the policy-based inference algorithm. So the whole idea here is predicated on the fact that if you had the opponent's policies, you can look at all the different actions taken in the history of the game. So this is all public information, and say assume that it was a given state, what was the probability that they took those different actions? And by treating all of these different actions in the history as independent events, I can multiply them together and then get a probability for that given state. And then if you do this for all the different states in this information set, using the exact policies of your opponents, you can actually get the true probability distribution over states, and then you can use this in your search-based algorithm. So some issues with this approach, so you might not have access to the opponent's policies, and it could be very computationally expensive. So to get over this problem, we modeled simple policies of opponents. And then there's a large number of states. So for example, at the beginning of card play, there could be up to 64 million different card configurations. So to deal with this, we sampled and normalized. So here's the algorithm. Yeah, it's just simply sample a subset of states from the information set. Then for each state, go through all the actions in the history, and then find the probability that they would have actually taken those actions given that that was in fact the true state, and then just multiply all those different probabilities together, and then just normalize at the end. So this will provide us with an estimated probability distribution for the states that we are looking at. So how did we get this, the opponent's policies? So for this, we used 25 million human games and then just treated this as a classification problem. So these human games are from an online Scott server that's open to the public, and we just, the Scott server is open to the public, so anybody can play this game online. And the labels were simply just the moves taken. And then we trained different networks based on different contexts of the game, and we trained all these networks using off-the-shelf hardware in under a day. And here's just the simple network architecture, so nothing too fancy, just 5 hidden layers fully connected. Yeah, so just a classification network, basically. So now we have policies that were based upon human, a large population of humans, and now we want to use that to perform inference in this game. So the baselines I'm going to be comparing against today are Kermit Inference. This is in the original paper back in 2009. It's just a table-based, use the same human data, a simpler approach, and it's just directly predicting the probability of the states. And then Card Location Inference, this is the work done in 2019. And what it does is it uses supervised learning to predict the location of all the different cards with a probability, and use that to directly predict the state probability. And then that brings us to the experimental stuff I'm presenting today, using policy inference. And I'll be looking at 2 different versions, which sample 20,000 worlds and 100,000 different worlds in the information set. So this card location inference was found to saturate at 500,000 card play configurations sampled. And this setup that I'm using takes a bit longer, so we haven't found the saturation point, but we can see that it's still improving when we sample more worlds. And the metric that I'm going to be showing off today to see the quality of this inference is just how many more times likely this inference is to sample the true state than selecting randomly. So this is just the TSR value, and just the idea is that if you're selecting randomly, you'll get a value of 1, and if you are cheating and you know the exact state, you'll get the an expectation the size of the information set. So bigger value is better. So here is the TSR values versus the number of cards revealed in the game. For this is the suit type of game, and this is soloist and defender. And you can see that all these top lines, these are all different variants of that this policy inference that I'm presenting today. And you can see that it is much better than the 2 other previous works. So it's significantly better in both. And the same thing held across all the different game types. And one other thing that you can see is that sampling more worlds. So the orange line is sampling 100,000 worlds, that's performing better. So we have some inkling that this hasn't saturated yet, that the inference will perform better if we spend more time in this process. So that brings us to the second bit. So we see that the inference appears to be significantly better using this process, and then the next idea is to look at how it performs, how it affects the card play in the actual game Scott itself. So for this, I used the baseline of Kermit with using these different, the search-based algorithm that I was talking about earlier, and this is using the different kinds of inference within the same algorithm. So the only thing different is the inference in the sampling step in the search algorithm. So it's just a card play tournament, and it's a mirrored setup, so player A will play against two versions of player B, so that's the soloist against two defenders, and then vice versa, with 5,000 matches per game type. And here's a top-line results from that. You can see, so this is the positive value means that the policy inference, so PI, performs better than the other player. And you can see that versus the original player, it performs significantly better for over the 3 different game types. And against the 2019 work, we can see that it also performs better. So you just have to take my word for it. These values do indicate a much stronger player in the game of Scott. And just this value over here wasn't found to be statistically significant, so more testing would need to be done. And this is just to show that sampling 100,000 worlds, which is over here, performs, improves the performance of this card player across the board, except for null, where it actually decreases the strength of the player. So this is actually interesting. We made the assumption that better inference will necessarily create a better card player, but this last value over here indicates that it's possible that using this perfect information Monte Carlo search-based algorithm, that better inference may not necessarily result in better performance. So this is an area to of further exploration. So yeah, that is the my talk. So basically, this policy inference vastly improves the inference in Scott, and then this better inference results in a stronger card player. And then future work. So the title of this was a policy-based inference algorithm in trick-taking card games. I didn't show its effectiveness in other card games, so some future work would be to test on different trick-taking card games. So specifically, looking at Contract Bridge would be a very applicable domain to see how this works in that, and to improve the sampling efficiency. So trying to get some more of the benefits, to push it further to saturation by sampling worlds in a more efficient manner. So yeah, thank you for listening, and any questions? Yes.
You mentioned 100,000 worlds.
Yes.
Is that at every move that we calculate that?
Yes, at every move.
Given history, how long does that take? I'm just curious. How long?
Yeah, and for sure. So, so at the beginning of when you get past this third trick, then the amount of worlds is actually less than 100,000 because it decreases exponentially. So at the beginning of the game, when you're actually doing all 100,000, it takes about 2 seconds on consumer hardware. So if you're playing just recreational against a computer, like that's enough to live. Like it might be a bit annoying, but it's still workable. But yeah, the previous one was a bit faster than that. Yes.
So thank you very much for your talk. May I?
Yes.
It's very interesting. I know this game is sort of, my impression is that the strategy for the defender, the one that are attacking, are totally different.
Yeah.
From the point of view of the defender, what they have to do is to reveal as little information as possible on their cards when they make the bid, and then the strategy on the other one, the attackers, would be to try to first to win, and then second to extract as much information from making the defender to reveal their cards. Is that correct?
So it's similar to what you're saying. Basically, the defenders, since they're working cooperatively, will try to provide as much information as possible with their movements, whereas the soloist is trying to give as little information with their card playing. So, yeah.
You see that explicitly in your strategy to
So did I see this in the policy that I was? So I didn't inspect the policy for that kind of properties. I'd expect it to be there, but that's an interesting idea to actually look to see the amount of information revealed to get some metric for that. But I didn't look into that. No. Thanks.
Okay.
Perfect.
So the next presentation is a self-play policy optimization approach with battery.
That's inside. 10 minutes?
I will give you a sign.
Okay. Oh, I didn't realize 10 minutes. Okay. Does this work? All right, 90 minutes. Okay. All right. So my name is Dan, and today we're going to be talking about self-play reinforcement learning, artificial neural networks, and Pokemon. So this was work that I did with Scott Lee. A little unfortunate that they cut the last word off of the program. But anyways, this project came out of a personal desire to train and implement artificial neural networks to learn how to play games. And when I started this project in late 2017, DeepMind was already out there with AlphaGo, and OpenAI had already started work on their DotaBot. So I wanted to basically see if you could apply the same thing to playing Pokemon. Okay, so what are we going to talk about today? I'm going to briefly go over what a Pokemon battle looks like. I'm going to talk about what makes building a bot to play Pokemon challenging. Talk about how we use neural networks to play Pokemon. We're going to go into some experiments that we ran, and then talk about what else we could do with this. Okay, so here's a Pokemon battle. Is there a pointer? That's fine. Anyways, so on the bottom left corner is me. The top right corner is my opponent. So I've got a team of 6 creatures called Pokemon, and so does my opponent. The buttons here are the potential actions I could take on any given turn. And there's a little bit of hidden state. I can't actually see what what Pokemon my opponent have until they come out. And we have our Pokemon start at full health and they battle out until one of them switches out or one of them faints. And this keeps going on until one side has all of their Pokemon lose all their hit points. So this screen cap actually comes from Pokemon Showdown, which is an open source simulator for the Pokemon game. The Pokemon Showdown is the environment that we use for all of our experiments. And the makers of Pokemon Showdown, they also run a public server where lots of people battle Pokemon over the internet. And for one of the evaluations, we benchmark our neural network against humans. Okay, so what makes Pokemon challenging to build an AI for? To motivate this, I'm going to describe a game that I believe to be much harder than Pokemon, which is Dota. So there are a lot of reasons why Dota is much more challenging. Here are just 3 of them. That said, there are a couple of things that are similar between the 2 games. There's zero-sum, there's imperfect information, and there are non-deterministic transitions. And because of this, you could reasonably expect that if OpenAI could make a bot to play Dota, we could probably also, using self-play reinforcement learning, we could do the same thing with Pokemon. That said, there is one key difference between the 2 games, and it's in the pre-gameplay team selection process. In Pokemon, it actually is much more challenging. So in Dota, you might have 2 times 10 to the 10 possible teams before the match starts.
Whereas in Pokemon, each creature that you battle with has around 10 to the 13 different configurations, and that's just one of them. You raise that to the 6th power to get the estimate for the number of possible teams. So this is very challenging, and team construction is a hard problem. In competitive play, people will typically construct one team and use it for tens of matches, and a lot of care is taken to make sure that their team is robust to exploits and just like robust to a lot of other things that, like a lot of other teams people construct. A side note that this team construction challenge is also present in games like Magic the Gathering and Hearthstone. It's just called deck construction in those games. And so the team construction really becomes like a game in and of itself, or one might call it metagame. Okay, so what do I mean by metagame? So in this setting, what we refer to means it means selecting the best team out of all possible teams. And when I talk about like the size of the metagame, really I just refer to the number of possible teams that are allowed by the rule set. So the different ladders on Pokemon Showdown have different restrictions around how you can construct your teams, so they have different size rule sets. And to make this a little bit more clear, I'll describe two of the ladders. The first one is random battle. And in this ladder, your computer randomly generates you and your opponent teams, and then you battle with them. So in this setting, there is no metagame because you have no choice over what teams you get to pick. And on the other extreme is the anything goes ladder. In this, there are no restrictions around what teams you can build, and there's a huge metagame. So what we work on in our experiments is a metagame of 3 teams, which is somewhere in between those two extremes. Okay, so how do we use neural networks to battle Pokemon, and what have people tried before? This is an incomplete list of things I found in my research. In particular, the first one and the last one are handcrafted value functions, and they also use like an approximate forward simulator for the game. Approximate because there's hidden state and you have to estimate the hidden state. In contrast, what we build doesn't use a forward simulator and uses a neural network to make decisions rather than using handcrafted rules. Okay, so what does training look like? If you saw David Silver's keynote yesterday, this process will look pretty familiar. We basically cycle through playing games against ourselves using the neural network as a decision maker, computing rewards for the actions that we took during the match, and then using that reward signal to update our neural network parameters. So what does the neural network look like? Okay, so here's a rough schematic. I'm not going to go too much into this. All I'll say is it's somewhat inspired by OpenAI's Dota schematic. If you want a closer look at this, go read our paper, and then I guess also read the source code. Okay, there are a few reasons why you'd want to use neural networks to create a bot. One is that you don't have to handcraft the rules yourselves, so it's a lot simpler. The other one is it's robust to small changes in the game. So if your environment changes a little bit, all you have to do is just retrain your bot. That said, there are a few reasons why you wouldn't want to use a neural network. One is that some experimentation to figure out the right architecture and the right hyperparameters is required, and that could be time-consuming and a little bit money-consuming. The other thing is that bad behavior is hard to debug. So if your bot is doing stupid things, good luck trying to figure out what's gone wrong. Okay, so now we've discussed how we train neural networks to play Pokemon. So I'm going to go into 2 experiments that we ran. And both of them, well, I'll just go into the 2 experiments. The first finding is basically we trained the bot on the random battle ladder, where the computer randomly generates 2 teams for both players. And
we trained it by using self-play. We left it running for about 6 days. Every so often, we took a checkpoint and we played it on the public Pokemon Showdown ladder. And we found that it improves as it goes on. It tops out at this rating they use called GXE, which basically is an estimate of if you play a battle with the average player, how likely are you to win? And we reached 72% on that. And nice thing about this is it costs around $91 on Google Cloud Platform. I mean, it's not nothing, but also it wasn't like millions of dollars. So the second thing we wanted to find out was whether we could have it learn to play with specific teams. And to do this, we hand-constructed 3 teams that are representative of strategies that are used in competitive play. The first thing we did was we took our bot that we trained here to try to play with these teams, and then we benchmarked it against a rule-based bot that we found online. And what we found was that, well, these are the results basically for each cell. We play 200 matches and record the win rate. Notice here, if the opponent team just picks the middle one, they'll always have a winning record. So not that great for us. The next thing we did was we trained our bot for another half day just with these 3 teams, and then we benchmarked it again against this rule-based agent, and we saw that it did the amazing thing was it did better in every single matchup. And this result might be obvious if you're familiar with deep learning literature, but it just shows that our neural network is capable of specializing and playing with particular teams. Okay, so what can we do with this? There are a few things you could do. I'm going to talk about 2 of them. One is we can definitely improve the neural network. There's still a lot of low-hanging fruit. In particular, one of the experiments we ran but didn't mention in the paper was that we just increased the width of all the hidden layers, and it got better. The other thing, which I think is more exciting, is potentially using your neural network as a team evaluation function. So the idea is in order to get a sense of how strong your team is, you train a neural network to battle with that particular team, and then you automate team strength evaluation by playing matches with that neural network. And as neural networks get better, players of the game, as they get better, they become better evaluators. And one of the things that makes this easier is that, like we mentioned earlier, you don't need a neural network to play well with every team. You just need one that can learn to play well with one team. Okay, just to wrap up, we talked about a lot of things, but the main takeaway here is that team building in Pokemon is a huge challenge. It's not solved just by using self-play reinforcement learning, but one of the things that self-play reinforcement learning opens up is that we can use these neural networks to largely automate team strength evaluation. Yeah, okay. That was it.
Questions or comments?
What was the reward function that you guys used?
So we use 1 if you won the game, 0 if you lost the game, and then there were a couple of auxiliary rewards. The auxiliary rewards in magnitude weren't over 1%, like 1% of the win reward. I think they were quite small in compared to the win-loss signal.
If I understand correctly, the feature space is quite definite here. So, I mean, the abilities of Pokemon and so on. So the question is, what's the decision of using such a computationally expensive method for machine learning? Because maybe you could use much simpler way than deep learning.
I think I mentioned that the alternative is to sort of, I guess there are multiple alternatives. One is to use hand-constructed functions, which is not really...
If you have a reward function.
Right, so here's the reward function. The reward function is much simpler to specify than specifying a bunch of rules for typing and other special moves.
No, I'm just saying, you
Yeah.
machine learning fine, but there are so many machine learning methods.
I see.
And you took the one which takes a lot of computational power.
Yeah.
So the question why?
So I think this is the one that provides this is the one that really provides the absolute goal.
I don't know.
No. I'm saying you're encoding the actual, by treating it as a reinforcement learning problem, you're encoding actually what you want, 1 if you win, 0 if you lose, as into the system, and that's I would say is a strong reward signal compared to using machine learning to do like a specific part of the game and then feeding that in. There are you could improve this by doing search, by also
you can use just old-fashioned neural networks. For example.
One last question.
You said there's something like 10 to the 13 combinations for a single Pokemon. How many of those are actually reasonable?
I think, actually, I would say probably around 10 to 13. So the combinations, actually, some of the unreasonable ones I didn't include in the calculation. For example, if you're familiar with the game like EVs and IVs, there are a lot of possible combinations for that, but I only selected 32 different IV assignments and around 100 different EV assignments. Whereas in reality, they're probably around 10 to the 6.
You're not talking just ability, you're talking about stats too.
Yeah.
Oh.
Sorry, you are welcome to ask him questions after. Thank you. So here comes the last presentation of this session. We all learn fast. Proximal policy optimization by Dino. Let me show you this. It's coming up here.
Okay, so I'm Dino Ratcliffe, and I'm going to be talking about win or learn fast proximal policy optimization. And this is some work that I did with 2 researchers, Katja, Hofmann, and Sam Devlin, who are at Microsoft Research. And the title's a bit of a funny one because you're either familiar with these 2 pieces of work and you know pretty much what this presentation's going to entail, or you have no idea at all. So just to sort of catch everyone up, win or learn fast, often abbreviated to WOLF, is a multi-agent RL technique for learning Nash equilibriums within games. And when it was first introduced, it was just used on tabular RL algorithms. And then proximal policy optimization is a policy gradient deep RL approach. And it's the approach that OpenAI used for their Dota 5 agent, which has shown very good results in a multi-agent environment already. But they haven't tested the specifics of how PPO gets to this great performance in the multi-agent environment. So a quick overview of the talk. I'm going to go over the background. There's quite a bit of it. There's going to be a lot of text on the screen. But I'll try and get through that quite quickly so that we can all get to the results and see what we came up with this research. And we'll have the approach and results at the very end. So for a bit of motivation of why we want to look at this, there are many complex games that have lots of agents that an AI would have to interact with. And these can involve agents that are constantly learning. So we're not just dealing with a stationary problem. Over time, our opponents can learn to exploit us. And this becomes a really hard challenge to learn how to combat against that. So what's a method that we could use to protect ourselves from this exploitation of these agents learning after we've perhaps stopped learning? And one of them is to learn a Nash equilibrium. So the really nice thing about learning a Nash equilibrium is it's a nice fixed policy. None of the other players can improve their payoff by just changing their policy. We can calculate a known minimum average payoff over time from our fixed policy, despite what our opponents will change as they learn. In some cases, the Nash equilibrium payoff can also be independent of another opponent's strategy. So something like rock, paper, scissors, if I play the Nash equilibrium of picking each action uniform random, even if I have a weak opponent that always plays rock, we will each win a third of the games. So that's one of the disadvantages of playing a Nash equilibrium, is we can't exploit our opponents as much. We can't assess that our opponent's playing a really weak strategy and exploit it. We just continue to play the Nash equilibrium. So for multi-agent systems, there are kind of two properties that have emerged from other research. One is rationality. So this is that we want an agent that is able to learn best response against a stationary opponent. So if we were against that opponent in rock, paper, scissors that was always playing rock, we would learn to deterministically always play paper against them. And because they're a stationary opponent, they're not going to change their policy when we play them. And this is quite a heavily researched area, because if you have a stationary opponent in a multi-agent environment, the environment basically breaks down into a Markov decision process. So any RL agent that can solve a Markov decision process is rational. The other property is a bit more tricky, and that's convergence. So this states that if we're playing against a learning opponent, we will converge to a stationary policy against that opponent. This is limited to our opponent being a rational agent, and in practice, we tend to use the exact same agent as the opponent. So, win or learn fast. Win or learn fast is an approach to get both rationality and convergence. And it does this by introducing a variable learning rate. So, when we play against an agent of the same type, we will try and decide which learning rate to use based on how well we think we're doing. So we'll have some estimated Nash equilibrium payoff, and then if we're doing better than we think the Nash equilibrium should be giving us in reward, we will actually slow down our learning to give the other opponent a chance to learn how to exploit that strategy. So we have two fixed learning rates, one for beating the estimate of the Nash equilibrium, and one for when we believe we're doing worse than the Nash equilibrium. An alpha win, which is the winning learning rate, is less than alpha lose. So I'm going to try and use this to demonstrate kind of how it works. It's a bit stretched, so it's going to be quite difficult. So if you consider the center of this plot as the Nash equilibrium, and the x-axis we'll call player X, and the y-axis is player Y. For player X, if the point is to the right of the Nash equilibrium, then it considers itself to be doing better than the Nash equilibrium policy would be doing at this point. If it's to the left of the Nash equilibrium, then it considers itself to be doing worse. And then on the y-axis, it's if the agent's below the Nash equilibrium point, on this plot, then it considers it's doing better, and if it's above, then it considers that it's doing worse. So what happens is this dotted line is showing how the policies converge to the Nash equilibrium using win or learn fast. So if we can see in the top right, in quadrant A, this would be a situation where player X is considering that it's doing better than the Nash equilibrium, so it has a lower learning rate, and player Y considers that it's doing worse than the Nash equilibrium, so it has a higher learning rate. And this has the effect of player X doesn't commit too far along the x-axis away from the Nash equilibrium because it's being slowed down by this lower learning rate, but player Y increases its learning rate, so it quickly brings its policy closer to the payoff that it expects from the Nash equilibrium. Just go over the other quadrants. So quadrant B in the bottom right, this would be a situation where both of them are considering from their estimate that they're doing better than the Nash equilibrium. So they have the same learning rate, so they actually just kind of circle around the Nash equilibrium. They don't get any closer to it. And this is what would happen if you had two fixed learning rates. So we'd see the agents just circle around the Nash equilibrium and not actually converge to it. They just go from deterministic strategy to deterministic strategy. And so we can see that the policy is actually getting closer and closer to the Nash equilibrium as we continue training. So that was Wolf, and I'll give a quick overview of PPO. So PPO is a policy gradient-based RL approach. We use rollouts to update the policy within a trust region. So if you know what TRPO is, PPO is kind of taking the same ideas and simplifies it. The reason I've put the loss up here is because it becomes important later. So we have the clipped policy loss, the value estimation loss, so that's for the actor critic part of the agent, and then we have the maximize entropy term. And this is explore exploit term. So it's basically giving incentive to the agent to play uniform random actions, and then as our estimations of the value increase and our policy loss becomes more important later in training, the entropy factor kind of gets overridden, so it can still learn deterministic strategies. So with Wolf PPO, what we try and do is we want to combine these two to see if we can use Wolf with modern neural network-based RL approaches and see if they still apply in this context. So all we do is we take stock vanilla PPO and we use these two different learning rates for if it's winning or losing. The way we estimate the Nash is we just keep an average of the payoff over the whole of training, and we use that as our estimate. So as we get closer and closer to the Nash, our estimate will actually get better and better. And yeah, we'll use the winning learning rate if our current set of rollouts have an average payoff higher than the average over the whole of training. So for the results, I'll just quickly go over the setup. It's a very small neural network, so as you'll see, we're using very basic games. So it's just two hidden layers of 20 neurons. We use stochastic gradient descent optimization. The standard with PPO is usually to use Adam, but because it has, it varies the learning rate, we wanted to take that out of the equation and just have one that has a set learning rate that we give it. And then for the difference between our winning learning rate and our losing learning rate was a ratio of 4. So our winning learning rate was 4 times smaller than our losing learning rate. So very quickly, the environments, we have matching pennies, which I'm sure you're all familiar with, rock, paper, scissors. Both of these games have uniform random Nash equilibriums. So both players are matching pennies. they should randomly pick between heads and tails, and you should randomly pick between rock, paper, and scissors in rock, paper, scissors. So these are the results. So we have matching pennies on the left and rock, paper, scissors on the right. Just to explain these graphs, on the left we have the blue area is standard PPO, averaged over 50 runs. The orange area is the Wolf PPO, averaged over 50 runs, and then the dotted lines are one example run from that, because they all sort of average out and give you a Nash anyway, but a single run will be oscillating between two different strategies. And you can see that in matching pennies and rock, paper, scissors. One thing to note here is the scale of the axes. So this is something we discovered, that PPO in this setting is actually quite good at getting a Nash. Like it doesn't diverge very quickly, certainly not as quickly as is shown for tabular reinforcement learning. And this is one with, we just increased the learning rate by an order of magnitude, just to see if we could see the gap a bit clearer between the two approaches. But the really interesting thing is the fact that PPO seems to do quite well anyway. And this is down to our entropy term that we talked about earlier. So this is trying to maximize entropy, which in this case, it's trying to give rewards for policies that are uniform random. And in both of these games, the Nash equilibrium is uniform random. So PPO effectively, for these two games, has a term in its loss function that is directly optimizing the Nash equilibrium for this game. So the way that we show this is that we then created weighted variants of these two games. So these push the Nash equilibrium away from the uniform random policy so that PPO no longer has a built-in optimization for the game's Nash equilibrium. So matching pennies, now the Nash equilibrium is to pick the head side of the coin just under half of the time. And for rock, paper, scissors, we change it so that rocks picked 20% of the time and paper should be picked around 40% of the time. And this has a dramatic effect on PPO and also has an effect on Wolf PPO. And we actually see that it now diverges a lot more within both environments. And these are the results tabulated for all of those. So we can see that Wolf PPO gets closer to the Nash equilibrium in all of the tests. So with the two separate learning rates and with the standard and weighted matching pennies. It's important to note that PPO and Wolf PPO both have this max entropy term, so they're both directly optimizing for the Nash equilibrium in the standard game. So Wolf PPO does also see a degradation in performance when we move to the weighted variants. And these were run over 50 runs. And in order to calculate these, we just took the Euclidean distance, and we took the furthest policy away over the last 10 policy updates to combat the fact that the policy will go around and through the Nash equilibrium at points, and we don't want to just happen to pick the point at which it went through the Nash equilibrium. We want to know sort of what the outer distance is of this circling. And so for future work, we'd like to extend the environments to more complex environments so that we can make proper use of the PPO aspect of this. Thank you.
Only one question.
Did you try comparing the Wolf PPO with the PPO trained with ADA?
So I have run tests with Adam, and they're very similar results. But for these results, it is stochastic gradient descent. But Adam didn't seem to have as much of an impact as we thought it might.
Okay, let's thank the speaker again and all of you for your